Awesome. Hello, everyone. Thank you so much for joining us today. I'm very excited about the talk that we have today. I'm very fortunate to have Sajeda Mokbel with us, and she's going to tell us about how physics is used in machine learning, or in other words, how can we make machine learnings that we use for physics more physical. Just a quick intro about her. She is doing her undergrad in physics with a minor in mathematics at University of Waterloo, and is a software development intern at Nuance Communications. And in the past, she has been software development interns at various places as well. So today, she's going to talk about how we are using simulations in physics very often to understand how different physical systems work, and use them for various engineering or environmental purposes, and how in recent years we have started using machine learning methods to enhance our simulations, because given the amount of data that we have the opportunity to use machine learning to accelerate and get results of simulations faster. But at the same time, we're running into the problem that machine learnings are just essentially looking for correlations, which means that they sometimes produce non-physical results. And there are three different ways that people tackle this problem. One is by adding a specific physical loss terms to the loss function to penalize for results that are not physical. Another method is that they identify a part of the simulation that is most computationally expensive and replace it with a machine learning method. And finally, there is this technique where they use to identify the underlying equations of motions for physical systems based on the data. And she's going to talk about two of these actually today. Without much further ado, I'm going to pass it on to her to go through the talk. Please take it from here.
Thank you, Amir. So as Amir said, I'll be talking about integrating physics into machine learning for scientific discovery, an overview talk. So I'm just going to briefly go through the topics of discussion. I'm going to start off by saying the goal of using machine learning in physics, the current limitations of using machine learning in physics, and then I'll talk about the two different methods that are being applied today in research to achieve this. So the idea is that machine learning models have had a lot of success in commercial domains, and there's hope for similar accomplishments in scientific disciplines. And there have been recently, but we don't want machine learning to only fit data to pre-existing models. We want to learn the model. We want machine learning to be able to learn the physical models themselves, and to be able to eventually replace them and maybe use them for scientific discovery in the future if they get very good. So some current applications to machine learning in physics today, it's widely used in almost all areas of physics. A few examples I can list are in fluid mechanics, where it's used to accelerate fluid flow simulations, or in particle physics, where it's used to classify neutrino events, or in condensed matter physics for phase transition detection. But there are a lot of limitations to applying machine learning in physics. The first one is that obtaining scientific data can be expensive, computationally and experimentally. So for instance, if you're running a simulation on a fluid flow, it could take a very long time to get converged results if you have a really complex geometry. Additionally, it can be difficult to generalize. So using the same example, I have two images of the velocity field of a flow past an ellipse, and then a velocity field of a flow past a much more complex geometry. And if you train a model for different flows past an ellipse or a cylinder, it could be hard to kind of understand the flow past more complex things. So it can be difficult to generalize. And another main limitation to applying machine learning in physics is that machine learning models basically generate statistical relationships between input and output variables to predict accurate solutions. And they usually do not have knowledge on the underlying physical laws. And that can create physically inconsistent data that can't actually be used in practice. So even if the results have less error, if they don't follow physical laws, they can't be used. And so I'm going to talk about the title of this talk says scientific discovery, and I'm going to be presenting equations that we kind of already know the dynamics for. So the reason why I say scientific discovery is that I feel that eventually, if a really good machine learning model can predict very general, can make general predictions for discovering underlying patterns to things that we don't necessarily know, such as neurons firing in the brain, it can actually lead to discovery of unknown patterns rather than just deriving the same equations of systems that we do know, like on the left of a double string. And so I'm going to be talking about the first paper that I read that is gearing towards understanding dynamics of the physical dynamics of systems through data. And that is called Sparse Identification of Nonlinear Dynamics, or SIND for short. And it was presented by Stephen Brunton and others in 2016. And basically, they want to turn measurement data into dynamics through this three-step high-level process of taking the data, measuring the time derivatives of the variables or coordinates of interest, representing a basis function, a basis of possible functions that can describe these dynamics, and then using sparse regression techniques to find a sparse vector that can represent these dynamics. The idea is that most equations that describe the dynamics of systems, they don't actually have that many terms on the right-hand side. And so they leverage this idea of equations being basically sparse in a basis of possible functions that it can be. And so this is a more mathematical representation of what I just said. So looking at equation 1, we want to be able to find f that describes the system. And we want to do that through equation 2, where theta is the library of possible functions it can be, times a sparse representation of it to derive these equations that can represent it. And when I say this library of possible functions, it can be just any general thing like polynomial functions with trigonometric functions, just anything that can describe the dynamics of the system. So given a set of high dimensional data, we want to find this function f that can describe it with the least coordinates possible. And so this model is applied to a Lorentz attractor example. So a Lorentz attractor is a highly nonlinear system that is described by the equations I have on the left. And as you can see, the right-hand side of each equation only has a few terms that describe these dynamics. And that's the idea they're leveraging here. So using the SIND model, we want to find this representation phi, and it'll only activate just a few non-zero terms that can describe it through the library of functions. And these are the results from the Lorentz attractor example. So as you can see, the true system had a sigma of 10, a beta of 8/3, and a rho of 28. And if you look closely at phi, you can see it got very close to the real underlying dynamics. And then reconstructing the identified system looks very similar to the actual results. So that's pretty interesting. However, in real case scenarios, given really high dimensional data like a reaction diffusion equation or a pendulum, we want to be able to discover the coordinates that can describe the dynamics by itself. So the Cindy model I showed you before, it works well if we know the variables that we want to measure to create these underlying relationships. But for many real world problems, we might not exactly know what can suit it best and what can describe the dynamics best. So we want to create a joint discovery of the coordinates and the underlying dynamics. And this was an idea presented by Kathleen Champion and others recently in 2019 that extends this Cindy idea. And so this is done using an autoencoder along with Cindy. So an autoencoder is a model that basically reconstructs the data that you put into it. And it does this by getting it to a very low level space of just the very few coordinates or nodes that can describe the data. And so we want to leverage this idea that in the latent space, we should have the coordinates that can best describe this data. And then we want to apply a joint discovery. So we want to use these coordinates Z in the intrinsic coordinates, and then apply Cindy to those to be able to find the correct dynamics of the model. And below each model, I have how you would usually maybe compute the loss. But this won't suffice for our system because if we train the autoencoder by itself, it might not necessarily find the relationships we want, meaning it might not be sparse in the space, in the basis space that we chose. So it has to kind of be a combined joint discovery. And that is done with the following equation. So it combines the reconstruction loss from the autoencoder, equation 1, and then it also calculates the loss of the time derivative of x with what is the reproduced data's time derivative to make sure it's getting the correct time derivatives. And then the latent space code Z, the time derivative of the Z variables in the latent space is computed to make it as similar as what's actually presented in the Cindy model. And yeah, so it combines all of these losses to create an overall loss function. The last term you see in the loss function is an L1 regularization term that promotes sparsity. And these are some of the results for the systems I showed you earlier. So it's pretty cool. I think it got pretty close to what the actual underlying dynamics are. So using just a bunch of high dimensional measurement data, it was able to predict kind of close dynamics. So for the reaction diffusion equation, the least amount of coordinates that can describe the dynamics can be given by two oscillating modes, which I found here. And as well as a nonlinear pendulum was actually able to predict the true equation pretty well. And so they also applied it to the Lorentz attractor example that I showed you initially. And so we know the true model on the left, A, and then the discovered model, B. You can see it's not really similar to what it's supposed to be, but it has the same amount of coordinates. Some of them are the right parameter. However, there's some differences between how Z2 dot and Z3 dot are computed. But what I thought was really interesting is even with this sort of not exactly correct discovered model, if you apply an affine transformation, it was able to discover a model that actually gets very close to the true model, except for the negative 5.5 term in front of Z1 and Z3 and Z1 and Z2 in the last equation. But the main dynamics are basically there, which I thought was really cool. And now I'm going to be discussing a different way this is done in research called the physics-guided recurrent neural network, which is a recent paper presented in 2019 by Gia et al. And so it aims to kind of, there's a popular model in lake dynamics called the general lake model, and it kind of aims to, that predicts the temperature of a lake given a depth, and it kind of wants to replace this with a recurrent neural network. So lots of processes in science and engineering have long-term temporal dependencies that a long short-term memory model can capture. So it introduces like additional variables in the recurrent neural network that keeps tracks of the physical states so that it can check for consistencies in the physical laws. And it does this by adding a physics penalty as well to the loss to be able to ensure that energy is always conserved. Yep, so this is the current kind of general lake model. Yeah, so it predicts the temperature of a lake at each depth given a date and some other variables such as wind speed or humidity on the date. And currently there's sparse ground truth date observational data for this. So I'm going to be talking, when I say observational data, I mean real data that was measured by a lake with sensors. And then there's the other data generated from simulations of the general lake model. So when I say observational data, I mean real data that's actually measured. And so it follows a long short-term memory structure. Just to very briefly explain. So a long short-term memory is similar to a recurrent neural network, but instead the way it generates the hidden variables, it takes into account more previous information by using a forget gate, an input gate and an output gate, and a candidate function to generate the hidden state. So it preserves more long-term information from previous states rather than just the state before it. And this is sort of the overview of how they constructed the physics-guided recurrent neural network for this lake problem. So they're keeping track of the lake energy and energy fluxes through time. And I have two equations, equation 1 and equation 2. So the first equation, so the change in energy depends on the energy fluxes going in minus the energy fluxes going out. So if there's more energy fluxes going in, it'll change the energy and eventually maybe increase the temperature of the lake. And then you can also calculate it by the energy of the previous time step with this current time step. So there's two ways to calculate these to compare it and to train the model. And the idea here is that these equations do not need labeled data to compute. So all they need is the input data, and I'll describe that here. I'm not going to go into too much detail of the underlying physics equations, but so for the first equation, this can be generated with the predicted temperature value y, and so just the difference between the previous step and the current step, and all other variables you see here are all just computed with the input data. So the area at a certain depth, etc. And the same idea goes for the second equation. So everything in the outgoing fluxes and incoming fluxes can be computed only from the input data, as well as some other estimations from Higgs collection of ocean and lake data, which we already have. So none of these need an output to compare to. So in the penalty, in the loss function, the loss function can be semi-supervised in this sense because it doesn't need all the label data. That's what I'm trying to say. And yeah, so this is their overall loss function. So they have the loss function LEC, which takes into account the physics penalty that I mentioned before. Yeah, so, and there's also this threshold term. So TEC, basically, sometimes energy changes are from processes that we don't really care about. So it has to be greater than a certain, the energy change has to be greater than a certain threshold to be accounted for. So they do that with the ReLU function. And this threshold number is generated through simulated data. So the average difference through the simulated data, they just add this threshold function so that it's not getting temperature changes that we don't care about. And then the normal loss function for the observed data is equation 2. And then these are combined to get the overall loss function. And this is sort of where they get their observed data. So they take training samples from different time periods as well as testing samples. So it ranges off many years. So this is their sparse observed data that they use. And they have pretty good results. So these are the root mean squared errors of different methods. We have the general lake model, so nothing to do with, this is just a physics model, no machine learning. The second one, which is a recurrent neural net, the recurrent neural network without the energy conservation, so without that physics penalty, and then the recurrent neural network with the energy conservation. As you can see, given enough labeled data, the recurrent neural network that is proposed has the least amount of error compared to the other two methods. So the percentages that you see at the top is the percentage of labeled data. So how much of these observed quantities do we actually put in? And you can even see just with 2% of the data labeled, it already has much better prediction. So that's pretty cool. And then they also do something else. They also try to pre-train the models with simulated data. And this is a method that I see happening not only in this paper, but other papers as well. So the idea with pre-training is they pre-train the model with simulated data from the general lake model. And because the general lake model is fully based on scientific equations and principles, it helps the model already have this sort of context beforehand before throwing it throwing it into the other data input drivers and just the observed data. So it helps a lot. You can see visually between the highlighted yellow and the highlighted green, it does improve the performance a lot. And yeah, so yeah. I think I can add my concluding remarks now. So I just briefly presented two different methods that are being used in practice now. And I guess the main takeaways is that the Cindy model with the autoencoder kind of proved the ability to learn dynamics of like really highly nonlinear system based only on data. And the physics-guided recurrent neural network is actually a very powerful framework for to predict variables just from spatial and time-dependent processes. And it can be incorporated in other fields like computational fluid dynamics. So instead of this energy conservation penalty, you can adjust it for whatever conservation law that interests you, so maybe conservation of mass. And it is effective with very little observed data, especially with pre-training from the simulated data. So I think that they all have pretty good results. And yeah, that concludes my presentation.
Awesome. Thank you so much, Sajeda. So let's talk about this a bit. All right, let's start from Cindy at the beginning. So I think I just try to check my understanding here. So what is happening there is the fundamental observation that the majority of physical systems, even if they are very high dimensional in terms of the coordinates that we know, are in fact have dynamics in very low dimensional manifolds, in low dimensional spaces. And that's what they're using to essentially get to this sparse representation of the dynamic space without even knowing what the equations of motions are. Is that what's happening there?
Yeah, that's exactly what's happening. Given given some sort of idea of the functions that can describe the system, you should be able to derive these underlying equations through the sparse regression.
Right. Interesting. And essentially the basic idea there is that you sort of calculate or measure the derivatives of the coordinates that exist in your problem, as well as the dynamics, like essentially how do the coordinates in this problem you're showing changes over time, and you fit into this equation that you're showing, the representation that you're showing, and calculate that Kissy matrix thing over there, which will tell you what the right parameters, like essentially low dimensional space, is that you're looking for. Sounds like a pretty straightforward idea, but nevertheless very, very interesting. But I think it becomes challenging when the number of dimensions becomes very large. Like, I think in this case, what we're looking at is probably one particle in a three-dimensional space. But if you're talking about a fluid, then you're talking about many, many particles in a three-dimensional space, which means that you have a ginormous problem to deal with, and that's why simulating those systems are difficult. And that's why we move to the second idea. Is that roughly the reason that we're using autoencoders?
Yeah, exactly. So we want to use an autoencoder because when you have this very high dimensional data, you might not necessarily know which coordinates will best describe the dynamics. And we can't assume that we always will know this in real scenarios. And so the autoencoder allows it to kind of discover it itself by getting the coordinates from the latent space from the autoencoder.
Very interesting. And essentially, I guess the fundamental intuition there is that autoencoders do sort of a manifold transformation from wherever your input data is sitting into a very low dimension, like hopefully the lowest dimensional space that is possible. And that's what you're using to select which dimensions to pay attention to, sort of like, I guess, typical dimensionality reductions that we use. And did they use any specific terms in the loss function here that helped them do this problem better, or were all of the terms in loss function as expected?
They didn't use any specific terms in the loss function, I don't think. No, it's, it's just the general reconstruction error, etc. Nothing specific. Maybe the regularization term at the end to promote sparsity, but that's all.
Right. And you said that that's an L1 loss, an L1 penalty to enforce the sparsity.
Exactly.
Right. And can you just do a quick recap of the two derivative loss terms there? What are we doing with them?
Okay, so equation 2 and 3. Yeah, it's looks like a very complicated way to represent. So the equation 2 is the time derivative of your original observed data minus the reconstructed axis time derivative. So they want to make sure that this autoencoder is getting the right time derivatives on the other output end. The third equation is in terms of the intrinsic coordinates. So we want the intrinsic z coordinate, so dz over dt, minus what you get from the Cindy model. So that the z, the initial z from the Cindy model. So they just are enforcing it to sort of have the same results on both ends. That makes sense.
Definitely. Okay, very interesting. Is there do you know if there's a specific reason that they're both looking at the loss related to the real data and loss related to the data in the representation space, in the Z space?
So why they're looking at both equation 2 and 3?
Mm-hmm.
I guess.
Why not just 2?
Okay, so I think, so for 3, we want to make sure that the latent space Z and the Cindy variable Z are pretty much the same, so that we're getting sparse coordinates.
I see.
And then equation 2 is to make sure that the autoencoder is really learning the correct dynamics by making sure the output derivative is the same as the input, is what I understand.
Mm-hmm. So is 3 then sort of the Cindy loss function?
Exactly. Yeah.
Okay, I understand. So essentially, they do the Cindy process in the representation space instead of the real space. I see.
Exactly. Yeah.
Okay, very cool. All right, let's move on to the next one, the physics-guided recurrent neural nets. To start, there's a question from the internet, from the live chat. Debasich is asking how resilient, I guess I'm interpreting the question, but how resilient is this model to parameter drifts over time? Like if you are simulating a system that has some parameters that you're learning using this technique, but that parameter is changing over time, would this be able to track that change? Do they say anything about that in the paper?
They don't elaborate on that in the paper. The only thing they're really tracking throughout time they chose was the energy conservation. So they don't elaborate that in the paper. But I guess if there is an important parameter that you want to keep track of through time, you can put that in through the LSTM maybe. But yeah, it's not expanded upon, unfortunately.
Right. I think from what I understand, one of the interesting things about this particular work compared to the usual ways that we do physical simulations is that estimating parameters is much more efficient and faster. Unlike in physical simulations where we have to do fairly large scale parameter searches to find the exact parameters that you want to use. So if there is, a parameter drift that you want to model, most probably in this case, it would be easier to do. But yeah, it's hard to know without knowing all the details of the model, definitely. All right, so they're using LSTM to replicate the physical evolution of the system. But there are two major problems that people mention about LSTMs. One is that, well, of course, it has a bit of a long-term memory, but that's limited. It's going to forget beyond a certain number of steps. But for physical systems, sometimes we need to know the dynamics that happened a long time ago to know what's going to happen to the system next. So how do they get around that problem in this case?
Yeah, so my guess is that because they're having this data that's over many years, so they're training through like a time period of 10 years and then another time period of 10 years later. is how they take into account all the different time change. But yeah, I think that's how they kind of see how it changes throughout time, I guess, through these 10 time periods where they get samples from.
Right.
Observational samples from.
Okay. And so that makes sense, but there is also another problem with, deep learning in general and LSTMs specifically, which is they are usually considered black box models, while for physics, especially if you're talking about scientific discovery, and one of the motivations of the paper is also the fact that if we are relying on machine learning to help us with scientific discovery, we should make sure that it doesn't tell us anything that is kind of garbage and non-physical. But if the behavior of these models is kind of not exactly interpretable, they're sort of black boxes, then how much can we really rely on that? Do they go into any details about what they're doing about that here?
So I feel like I thought the same thing too, and I feel like how they further enforce more learning of the scientific equations that underlie it is through the pre-training with the physics model. And this is something that I've seen in other papers as well, either like pre-training with the actual physics model that relies on all these equations, and then incorporating it into a machine learning model to accelerate things, or doing the machine learning model part first and then putting it into a physics model to further enforce these scientific relationships. And yeah, so I think that they do this they kind of want to solve this by the pre-training with the physics model, like some sort of combination of using the physics model, like the real physics model.
Right. So essentially, I guess what you're saying is that this whole combination of these machine learning models with physical models, either using the physical model to provide pre-training data, or getting the output of the machine learning model and putting it into a physical model, or what they're doing here, like adding that loss term to constrain the output to be physical. It doesn't really help us with interpreting the result, but rather it is helping us, constrain the problem to be physical at least.
Yeah.
Is that a good summary of what you said?
I think so, yeah.
Okay. And since we're on this slide, I think the interesting thing for me here was that adding the pre-training really made a difference in, like, adding the energy conservation did not change the accuracies, the error rates significantly, but adding the pre-training significantly changed that. And and they are using this to claim that this means that they can train models much better with less data, with less labels. Can you talk about that a bit? I'm not sure if I completely understood what was happening there.
Yeah, I think that they're saying because of that term in the loss equation that does not need labeled data, you can train the model with good results with very limited observed data, because there's like this physics penalty in the loss function that contributes to the learning that doesn't need observational data. And then with this pre-trained model, I believe the pre-training requires even less labeled data to achieve good results, because when you're pre-training it, so I think that in machine learning models, the weights or parameters are like first initialized, and if they're initialized poorly, it can take longer to get good results or not get as good results. But with the pre-training, it helps with the initialization as well. and makes for better results.
I see.
Yeah.
I see. So I guess, again, to check my understanding, what you're saying is that usually you would need more data in training more labels in training machine learning models, because the initialization is normally random, and it means that you're somewhere weird in the space of the problem, and you need more data to find your way down to the local minimum the global minimum that you're looking for. But in this case, using the physical simulation that is not really data-driven, it's just a physics simulation, doesn't need labels, helps you initialize the parameters of your model more effectively, and therefore you converge to a better result much faster with less data.
Exactly.
Very interesting. Okay, Daniel is commenting that you should look into symbolic regression if you want to infer the underlying formula. So I guess that's another approach to look into as well. I actually saw a paper on this topic a few days ago. You should take a look at it. All right, so I guess another confusion that I have, and maybe you can help me understand it better, is in what we are talking about, we are doing a simulation first and use the data of that simulation to train a machine learning model, and then constraining the loss function to be physical. Constraining through the loss function for the result to be physical. But if we can do the simulation, why are we doing the machine learning at all? Like, why don't we just continue with the simulation if it is already working?
I think that machine learning models can produce converged results faster than simulating data. And also, I think from what I understood in the paper, they didn't use too much. Actually, no, you're right. Sorry, yeah. I think the idea is to be able to replace these physics models because sometimes they take a long time to converge, and with a trained machine learning model, it could introduce faster results and sometimes more accurate results, as you can see here.
I see. So I guess, in other words, we are interested in doing machine learning because it would potentially speed up our simulations. Like, instead of having to do larger scale simulations that we normally do in physics, now we can rely on the machine learning to just learn it from the data. But we know that the pre-training is helping with initialization, as you just said. So potentially, what we can do is to do the pre-training, to do the initial simulation on a smaller scope, more limited, something that we can do quickly, just for the sake of being able to do better initialization, and then leave the rest of it to the machine learning model, which is a very interesting approach. All right, let's see what other questions I have for you. Let's check online. All right, online people, if you have more questions, please put them in the chat. Okay, so what are they do talk about generalization of machine learning models versus physical simulations. Like, physical simulations, we like them because pretty much everything is under control, and we end up with some fundamental, like, they either start from some fundamental equations that we know they generalize relatively well. But machine learning models usually suffer from generalization. A lot of time they overfit. What are your thoughts on the generalizability of these approaches compared to the pure simulation versus pure machine learning models?
Yeah, so in terms of generalization, they actually had a section about this on this paper as well, where they did different lake geometries, like a normal cone and then like the shape of a martini. And they got okay results for different geometries. So it is kind of generalizable. I'm not too sure like with how far generalization goes, because I feel like it can just be general to a certain extent. Like this machine learning model can probably be used for other lakes with somewhat similar geometry, but nothing too widely different or not very, very different climate conditions. And the equations that are, yeah, I think that's what I mean. Yeah, I think it's just like generalizable to an extent, and that's how it is in other fields as well.
Mm-hmm. Okay. I think large scale physical simulations also suffer from generalizability a bit because, like if it was as simple as just following the equation, it would have generalized as much as we wanted, probably within limits and the assumptions of the problem. But when we are doing simulations, you have to put in a bunch of parameters by hand or do grid search to find them. And that usually has the overfitting problem as well. So definitely the combination of the two probably generalizes better, but it's still, as you say, within the limits of the assumptions we are making. An interesting thing that they say in the paper, in the physics guided neural net paper, is that this, they don't really go into details, but I'm curious if you have intuition, and if it is a curveball, we can ignore it. But they're saying that they think there might be some architectural enhancements needed to LSTM for this kind of purposes. Do you have any intuition about what they're looking for there?
I'm not entirely sure. My guess would be maybe the LSTM has to be changed to kind of include more physical constraints and laws to it, because all they really keep track of is the energy conservation. But I didn't look too much into that area. I don't have any wild insights. I'm not too familiar with the LSTM architecture either. It's just a brief, I've never worked with it. Yeah. But my guess maybe like to include more scientific equations in the process, maybe.
Yep. I guess that's an interesting thing to investigate to see. My guess is that what they meant was, what if we could make changes to the architecture so that the results are more physical rather than just adding a term to the loss function? Because adding the term to the loss function is sort of a post hoc treatment of the problem. Like we go all the way through the problem, then look at the results and say, oh, this wasn't good. Let's go back and fix it. But if the architecture, natively by design, captures the physics, maybe it would produce better results and or faster results. So yeah, I don't know either. So I'm guessing as well. So another question from Omid online. He's asking, I guess I'm interpreting again, there are all these explainable AI frameworks that are coming out. Have you seen, anyone trying to use those in the context of scientific discovery?
From the papers I've seen, I haven't seen any explainable AI models applied to anything. I've just seen this similar idea of adding a physics-based penalty. And then I saw the Cindy method, which is something different that I've seen, but nothing beyond that from what I've seen so far.
Right. Yeah, from my very short, maybe 1 hour research this morning, also, it seems like there are three approaches, two of which you covered, like the physics guided with the loss term, the discovering underlying equations based on data, and the third one is replacing time-consuming parts of the simulation with machine learning models. and I haven't seen a lot of explainable AI kind of approaches. And I think probably it is physicists that are doing this kind of work mostly, and we don't really like sort of post hoc explainabilities. Generally speaking, I guess we prefer to have the simulation part still somehow involved, and that's kind of explains why there are all of these approaches rather than sort of post hoc explainabilities like Lime, etc. All right, that's all the questions. I'm going to give a minute to online people to drop in any other questions that they have in the chat, and try to summarize what we talked about very quickly while we wait. So essentially, we talked about two methods. One was based on the intuition that the behavior of physical systems is usually based on very low dimension, like dynamics on very low dimensional manifolds, and essentially used an autoencoder with a sparsity, what was it called? Sparsity induced nonlinear dynamic simulation, regression, to discover the underlying equations of motion of the system. It's called Cindy, which was very cool. And then the second one, what we did was adding loss terms that are inspired by physics. In this case, specifically difference between the energy flux going into the system and energy flux coming out of the system, to penalize for giving non-physical results. Oh, there is one question. Did I get it right? So Krishnan is asking, did I get it right that physics-based loss function can help reduce the need for labels? Can you elaborate on this, please?
Yes, I think in this case, the physics-based penalty helps reduce the need for labels because the difference in energy can be computed without a labeled data. So usually in the loss function, you compare it with a labeled data to get more accurate predictions. But the energy equations were all derived from variables that don't need labeled data. It just used like a Higgs collection of ocean and lake data, heat of vaporization, area at depth, et cetera, et cetera. So all of these terms don't rely on the labeled data. That's why it helps with a reduced amount of labeled data.
Definitely. I think the difference was relatively small compared to using pre-trained, yeah, I guess the next slide, yeah, like compared to using pre-training the model based on a physical simulation. So definitely, you know, as you said, the energy conservation helps with better results, but on top of that, the pre-training can even take that further and help even more.
Yeah.
All right. Do you have any last words? Do you want to summarize anything or add any thoughts or comments?
No, I think that concludes everything.
Perfect. Thank you so much for doing this talk, Sajeda. And thanks everyone who joined us online today. If you enjoyed this talk, please do go to ai.science and create an account to see all the awesome talks that we have coming up. We have 3 to 5 sessions like this every week, in addition to a lot of other activities that we do, including our Slack channel that we can join and talk to the community. And make sure you subscribe to our YouTube channel, ML Papers Explained, as well, and hope to see you in the future sessions. Thanks again, Sajeda, and very excited to see all the sessions that you're going to organize going forward on this topic.
Thank you.
Thank you.